Okay, we'll first start with the confusion matrix. Does anybody here have any doubts regarding this? Like broadly speaking, any doubts regarding what a confusion matrix is, how does it work, how to interpret it, and so on?
So I didn't attend the last few lectures, so I don't know if it's a waste of everyone's time if you have to repeat, but in case it's okay if you can just give a summary.
Of the last two live sessions, is that what you're
Yeah.
asking?
No, no,
Okay,
no.
last.
The confusion matrix, right? In case it was discussed.
No, no, that was not discussed. This is a new topic.
Ah, okay.
In the sense, in last week, classification models would have been introduced.
Hmm.
So that would have been covered, but today we'll focus more on this evaluation metric and we'll be covering it fully. I just wanted to know if you guys already have some idea about it, and based on that, I can pace it. Anyway, so let's, yeah, sure, that's fine. We'll begin this session as is. So the setup is that we are going to look at a classification problem, and primarily we start with the binary classification problem, wherein we have two classes and we want a model to predict the samples correctly to one of the two classes. Now here the classes we have are cats and dogs, and to show some sort of sample images, the one on the left is our images of cats and the one on the right is our images of dogs. Now, coming to say classifying it, we first have the setup wherein, if you look at it, say this is what our model has predicted. Now we have finished training, we have imported the model, we have instantiated it, we have called model.fit on the training data, and while predicting on the test data, this is what it has done. The first two images you can see it is of cat, but the third one it ends up classifying a dog as a cat. Likewise, in the other one, sorry, likewise, just 1 second. Yeah, in the other one, it has classified the image of a dog as a cat instead. Here. Now, if we were to build a confusion matrix for this is what it would first look like. Depending on how many classes we are going to have them as rows and columns here. So since this is binary classification, we just have cat, dog, and here a dog and a cat. We have true labels on one side, predicted labels on one side. Now here again, there is nothing as such as to which has to come where. It is just a matter of convention. In the case of sklearn also, you'll have to see where exactly it comes, and based on that, you'll be inputting the values. Now, the cell that would be filled here is if the true label is a dog based on this, and if the predicted label happens to be a cat, then you would want to put that image here. So, okay, in this case, we have first taken true label cat, predicted label cat. We are happy with it, so it was the correct image. Same with true label dog, predicted label dog, it went to the correct one. But here we had the true label as a dog, but the model predicted it as a cat. So now this is a misclassification. Specifically, it is a misclassification where the true label being dog, it is predicted as a cat. Now these things become more and more relevant as we have more classes. And then so on it continues. So in this is the entire final setup, so to say, wherein we have our true predictions along the diagonal and our misclassifications along the other diagonal. Now this thing we can sort of have a look at this in the case of the MNIST dataset as well. Now you might have already seen the MNIST dataset. If not, you'll be seeing more of it in the next week, wherein it's a collection of 70,000 images, wherein the digits are handwritten. Now this one is present as a 28 cross 28 image, and when you flatten it to a row, you end up getting 784 features. So this way, even though it is an image, we can represent it in a tabular format. Now, what exactly will be the values? It is going to be a value between 0 to 255, which will be indicative of sort of the color. Okay, so this is the actual data set. And now say we build a predictor wherein our objective is to identify whether the image is of digit 3. So now this specific one was actually something that was used, I think, in the case of post offices or something to sort out the zip codes. Now here is our version of confusion matrix for the MNIST dataset. Now as you can see, we have in the diagonal, this time we have true negative here, true positive here, false negative here, and false positive here. So the left one says actual for true labels, and this is the predicted labels. And yeah, if it was a 3 and it is actually a 3, it is here, and otherwise the images are present here. Some mistakes that it has made is the number 8 also, which has to be negative, it has predicted as positive, which is that it is class 3. Likewise, we had 2 digits of class 3 which are supposed to be predicted as positive, but it ended up predicting it as negative. So this is how we read it. Now, as you can see in this premise also, it very much, what we call as positive and negative depends very much on our objective. Now here we said it is to predict 3, which is why we've taken it as a positive class. Again, this is just a matter of convention. We can say we are building a model which does not want 3s. So then you can treat your 7124 or whatever is there here, non-3 digits, that is digits between 0 to 9 apart from 3 would have been considered positive. So this is just a rough outline of it. Now, this is the case where it's a multi-class setup. Here you can see instead of having label names, we have simply as 1, 2, 3. So there would have been 3 classes in this multi-class classification setup. This is why we have 3 rows and 3 columns. And if I were to pick, say, this number, this simply says the original label of the data point was 2, but our model predicted it as 3. And we have 3 such samples. So the sum of the entire confusion matrix is the total number of samples. The diagonal will be the true predictions for the different classes. The rest of them will be misclassifications. Now, let's just build it very quickly. So for the case of binary classification, this is how you would have the 2 things. Now, even if you were to try it in sklearn, when you import the evaluation metric and pass in your ytrue and ypred, it basically takes in these 2 arrays and it makes a comparison. So now when it comes to true and predicted label being 0, we had 4 samples, which is why the number 4 goes here. If it is 1, the true and predicted label being 1, there are 3 samples, so it goes here. And then we come to misclassification. The true label is 0, but predicted is 1, so it goes here because the true label is 0, predicted is 1, so we get 2 samples here, and the remaining 1 sample goes here. Now, the same thing happens in a multi-class classification setup. You can check this out. So here, true label for 1, let's see, there's 1, 2. So there's 2 here for true and predicted. And for misclassifications of 1, we'll see. So when true label is 1, 2 more misclassifications have been there. So here 1 is predicted as 2, hence the 1 here. And 1 is predicted as 3, hence the misclassification here. So far, is it clear how the confusion matrix works? Okay. Now, can you think of how this would be useful and what would be your insights from this? So you built your classification model, you got some output. What would be your comments after, say, building this confusion matrix? What would you tell someone who reads or reads through your work? What could be some insights?
How accurate is your, how the model, how accurate it is in predicting the predicting whether it is a dog or a cat or a dog, whatever it is, how accurate it is in doing that.
Okay, what do we mean by accuracy?
Means how many correctly classified things are there? How many samples it has correctly classified divided by the total number of samples will give the accuracy of the model.
Correct. So we'll be getting to that anyway. But say if you do not know you've not yet gotten to the part of accuracy. Without that itself, is there something you can say? Something very straightforward. Okay. So what you would end up doing when you are building your notebooks is that once you have this classification, once you have this confusion matrix, the first immediate observation you will have is how has my model performed for different classes. Now, quite often, if you will see it when you maybe in your classification assignment, you might have seen some. If not, when you're doing this current Kaggle assignment or maybe any other data sets you work on, you'll end up seeing it more often. You'll see that your classes might perform well on certain classes and not so well on the other classes. Now, this becomes more prominent when there is imbalanced data set. What is imbalanced data set?
Where
When the
the
data,
labels are not uniform, number of
yeah,
samples of each label are not uniform.
Correct. And why would a model have an issue with something like that? Why would the model have an issue with imbalanced data sets?
Because it will rely more on the samples which are having labels which are having higher number of samples.
it will
Okay.
tend to overfit. Yeah.
Okay. So what you're almost there. What actually ends up happening is for these things, what we mostly need is data. So the more data we have, the better the model performs. Now, since it does not have enough samples to make out about the lower class, on comparison with the majority class, for which it has a lot of samples, it can tend to rely more on predicting everything as the majority class. So that is the case where we have an imbalanced data set. And do you all recollect any methods to handle imbalanced data sets? Okay, so there's a few approaches you can go when it comes to imbalanced data sets. One of them is to change, like in your training data set itself, you start creating samples so that it matches. So one is you have your systematic minority oversampling technique through SMOTE, and the other one is to undersample it. So one is you can oversample, wherein you duplicate the samples of the minority class to make it match the majority class. The other is you cut down the samples that are there in the majority class to bring it comparable to the minority class. Now, the in practice, when you end up using it, it's not always the case that it is going to end up performing well, at least for classical models. So this is again something you're going to try out, and if it doesn't work, then you give a statement that okay, this is the method that was tried to sample, but this did not assist in improving the accuracy of the model. Now, a couple of other methods include, one of them is to make use of class weights within models itself. We'll have a look at it today, wherein the model itself is going to take into account how many samples are present in different classes, and it is going to weigh those samples accordingly in its model building. Now, a third approach is wherein while you're training your model, you can train it for certain evaluation metrics. And can you think of any evaluation metrics that do not get affected by imbalanced data set? Okay, so this is also something we'll be discussing later today. We'll see what evaluation metric has an issue with imbalanced data set and what doesn't. So broadly, that is what you would get out of this confusion matrix. It gives a very quick view as to on what classes your model has performed well and on what it hasn't. And this is something you will give out as a statement. So now you know that okay, if say my model has not done well on class 1, I need to see why it is making mistakes when it comes to class 1. Maybe it has some poor data when it comes to class 1, maybe it does not have enough samples. So this is how you would further analyze to improve your model. Okay, so okay, this is the first one. Now once you get a confusion matrix, you can say that all images of dogs have been correctly classified, wherein let's say dog was of label 1 and cat was 0. Now the statement is correct, but would you call this a good model?
No, because it has predicted the cats also as dogs only.
Correct. So all in all, this model has not really made any prediction. It just said everything is one class. So this would be like, even though this statement is not incorrect, but you can clearly see that this is not good enough for us. Now this will extend sort of to the imbalanced data sets example. The other is the case where when you see this, if you end up seeing the values are like this, once again your model is not really doing that well. It is just randomly guessing some class, and this is how it has performed. So in this way, you can interpret the values of confusion matrix, and it gives a good sort of presentation and insight towards how your model is doing on the data set. Okay. So the other evaluation metrics that we have, let me just open that up. Okay. So first we'll start with precision. Can anybody tell me what precision is? Okay. So precision is defined as the ratio of true positives to true positives plus false positives. Now this is the problem when your model falsely predicts the class to be positive even when it is negative. Now in this confusion matrix, we take class 1 as positive and class 0 as negative. So that time you would have 87 here in the numerator because this is the true positive, divided by 87 plus 3, 90 for where it is predicted as 1, and this gives you a precision of 0.966. Very, very straightforward calculations for this. Likewise, in the case of why is accuracy there after this? Okay, we'll go with recall first, maybe. So there is recall. So recall is nothing but the ratio where it is true positive divided by where it was true positive plus falsely predicted as negative. So in reality, this should have been positive. There are 6 samples where the true label is positive, but the model has falsely predicted it as negative. So now this tells us how many samples our model has missed from predicting as the correct class, whereas in the other case, how many of them it has incorrectly predicted as positive. So now both of these have issues. So one example that we take is, say for example, the credit card fraud dataset. So in this credit card frauds, the number of frauds compared to actual transaction tend to be very low. So you might have millions and billions of actual transactions, whereas a very small percentage of it end up being fraudulent. So now you might have 2 cases in mind. One is that I don't want to let any fraudulent transaction go unflagged. So if there is a fraudulent transaction, I will flag it and I will initiate some investigation. In that case, you want your model to have a lower number of what? False positives or false negatives. Let's
False positive should be less.
okay. Let's describe it. So you work for a credit card. You work for a bank. The task is to monitor fraudulent transactions. If a transaction is fraudulent, you mark positive. If it is genuine, you mark negative. Okay, this is the basic premise. And case 1, you do not want to allow any fraud transactions to go unflagged. Okay, so this is the setup. Now, firstly, what is going to be true positive?
It's a fraudulent transaction and you have flagged it.
Okay, transaction is fraud and model has flagged it as fraud. True negative.
Transaction is normal and it is
Okay.
genuine, and model has flagged it as genuine.
Okay. Next we'll go for false positive.
Transaction is genuine, but model has flagged it as fraud.
Okay, is that right? Any other answers? Okay. So false positive is when the transaction is actually genuine and model has flagged it as fraud. False negative. What is the remaining case?
Transaction is fraud, but model has flagged it as genuine.
Okay. So this is our setup. Now for case 1, what is the one that we have to focus on?
False negatives.
Okay. So why false negative? Because what we said is that we do not want any fraudulent transactions to go unflagged. So in the case of false negatives, even if the transaction is fraud, we are flagging it as genuine. So do we want more of this or less of this?
But less of this.
We want less of this. But then if you look at it, what we are saying is I don't want any fraud transactions to go unflagged, which means what am I okay with?
False
Among
positive is okay, but false negative is not okay.
Correct. So what we want to end up doing is we want to reduce false negatives, wherein we end up in the case where we let fraud transactions go. But we are okay with if the transaction is genuine also, but we are flagging it as fraud. So in this case, which one is a metric that we would want to focus on among precision and recall?
Recall?
Why is it recall?
Because in the denominator in recall we have false negatives, right?
Okay, so that is right. So this is because when we take recall in the metric, we are also taking false negatives into account. So now if my false negative is very high, what will happen to the recall score?
It will be low.
So
Correct. So when this true positive is something we want to be high, we want it to be high regardless. Now if false negative is very high, that means the overall recall drops. Likewise, if false negative ends up being 0, then we have a perfect recall score of 1. So in this first case, if you do not want to allow any fraudulent transactions to go unflagged, and if that ends up becoming the case where we want lower false negatives, then recall would be a good metric. Now in some other cases, we can have a case 2, wherein you care about customer satisfaction and you are okay with minor frauds being unflagged. Now in this scenario, again, if I've defined this as positive and negative, in this particular one, my concern is that I wouldn't want genuine transactions to be flagged as fraud. So in that case, I wouldn't want to have too many false positives, which is controlled by precision. Okay. So then we have accuracy. Accuracy is what I think Siddharth already mentioned, wherein we just want to know how many predictions it has gotten correctly in total divided by all the predictions that it has made. So that is nothing but the sum of this diagonal, which are nothing but our true predictions, divided by all the predictions that it has made. Now,
So sum of the diagonal entries divided by the sum of all the squares, right?
correct, all the values present in the matrix,
Okay.
which is nothing but true positive plus true negative divided by all these other things. So now, what is a scenario where accuracy might not be a good metric? So can you think about in what cases would accuracy not be a good metric? Okay, so let's take this case. Uh, let's go with the credit card fraud scenario itself. Where we have, say, uh, 1 lakh genuine transactions. Okay, so this is our scenario. Now, can you think of, would there be some issue when I do model training here? Firstly, what is this sort of data set called? And what could be an issue when I do model training? And how would that translate to the idea of accuracy?
So some of the fraud transactions, even if they are not flagged, and still will get a high accuracy. Some of the fraud transactions, even if they go unflagged, still will get high accuracy because most of the transactions are genuine, which will be flagged as genuine, which will be taken
Yeah,
as genuine.
it's a biased data set.
Sorry, yeah. So here what we have is an imbalanced data set. And as mentioned, if I were to predict everything as, say, a genuine transaction, this would be my accuracy. So we have accuracy equal to, so we have true positives plus true negatives. Let's say it predicted all of this as genuine. So the genuine transactions, it has still predicted genuine. So in terms of true positives, I'll have my 1 lakh. But in terms of true negatives, I'll have 0 because it has predicted everything the other way around. And when I'm going to divide, the total sum of predictions that I'm going to make is nothing but, yeah, this and then 500 here. So now if we see this value, this is still quite high. Okay, so of course, when this connects and runs, you'll see that it will still have a very high accuracy of over close to 99% itself. But we know that this is a bad model because it cannot really catch hold of any fraudulent transactions. Now, on the other hand, the case that we considered is where we don't want fraudulent transactions to be flagged as negative. That is when we cared about false negatives, the same thing would start looking a little different. Wherein if I take the negative one of the classes, we first start with 1 lakh and for the true positives, and the false negatives would be 1 lakh plus we would have another 500 in this case as well. Now this is so now this is the calculation for recall. Is anyone okay with why this is the calculation for recall? Are there any doubts here? Okay, so now this is recall for the positive class. Now we just discussed that recall is a good metric when we for this scenario, but it seems to give a high score. So what would have been the issue? So why is it that recall is useful here? Okay, this is where the advantage of recall comes, wherein we are going to calculate it for both classes. So if we were to do recall for the negative class, now since it has 0 correct predictions, so the formula, it changes now to true negative divided by true negative plus false positive.
False positive.
Okay. Does anybody have a doubt as to why this is? So this was the recall, but this was specifically for the positive class. So which is why it was true positive by true positive plus false negative. However, if I want to calculate the recall for the negative class, then it becomes true negative divided by true negative plus false positive. So if I were to implement this now, the true negatives are 0. And then only thing is that the false positive ended up being 500. But this model is now pretty useless to me because it has a recall of 0. So this is a good way to capture whether the model is doing well for imbalanced data sets. Now we'll quickly continue with the other evaluation metric that we have for classification, which is F1 score. F1 score happens to be the harmonic mean of precision and recall. And if we were to individually write down the sort of formula we have for precision and recall, this is what it translates to. Any doubts with the content so far? Okay.
So F1 is used where both recall and precision metrics are evaluated. I mean, it gives a
Correct.
balanced kind of.
So F1 score is what we generally prefer for imbalanced data sets because it is a combination of both precision and recall. And the thing is, we just saw that here when we calculated the recall for class 1, we still had a very high value. But now if I calculate precision for this same thing, my precision would again include, precision would give a score of 1 and this would give, recall would give a score of 0.99. But when I make use of the F1 score, I can calculate different versions of the F1 score, where one of them will strongly punish the models that predict everything as one class. So in such cases, we are going to see it through the use of classification report. Therein it will become more clear. Even if the model does well in, say, one of them, precision or recall, since F1 score is a combination of the two of them, it will end up having a much worse F1 score. Is that okay? All right.
Okay.
Now the extension of these things is quite straightforward for multi-class classification as well. So here we have 3 classes. So accuracy remains the same, wherein it's going to be correct predictions divided by all predictions. So in the diagonal, we have the true label being 1, predicted being 1, true label being 2, predicted being 2, true being 3, and predicted being 3, as is. So I'm going to sum up these 3 things divided by the total number of predictions, and that gives you the accuracy. Now, when it comes to precision, however, you have to recollect the setup that we had for that MNIST digit classification. Now we want to consider only class 1. So the true positive now, the positive label is 1. So true positive happens to be 16. And anything else that it has falsely predicted as 1. So you can see the false predictions of 1 in this column, wherein the label ended up being predicted as 1, but in reality it was of either label 2 or 3. So anything else, it does not matter whether it is class 2 or class 3, but our model, if it has falsely predicted it as positive, and in this case we are taking 1 as positive, we take it for the count of false positive. Okay, so this is how we get the precision for class 1. Now when we do for class 2, it is as though class 2 is a positive class. So true positive is once again 15, and false positive is wherever it is falsely predicted as 2. So you have 2 samples here and 4 samples here, giving a total of 6, which is why you have the value 6. The same thing continues for class 3, wherein now this is the positive class and you have 5 false positives giving this score. You extend this idea to recall as well, wherein for whatever class you are taking, treat it as positive, then use the formula that we have discussed previously. Now F1 score, in this you are again going to have to calculate it for different classes. So you have F1 score for class 1, for which you are going to use the precision for class 1, recall for class 1, and then get the F1 score. Likewise, you do the same thing for class 2 and 3. Now, if you want a combination of all of them, you want to see all of them together, what you're going to need is the classification report. So the classification report is a snapshot that provides these details in one go. So here you can see we have calculated precision and recall for class 1. Then using the same formula above, it has calculated the F1 score for class 1. Now what is the support that is present here?
The number of samples with class 1.
Okay, and what is the total number of samples in this data set?
50.
Yeah, so that's right. So we have 3 different classes. So this says there are 20 samples for class 1, 20 for class 2, and 10 for class 3. And this one that you see here is the sum of it all. And then you have the accuracy here, which is just the sum of correct predictions divided by whatever it has gotten incorrectly. So for that we have just one value. Then there are two different sort of variants that we can calculate called macro average and weighted average. We'll see a bit more of it later. So this has to do with, this takes into account support as well. So how many samples were present and then does the calculation. So far, is this clear? Okay. So now, what is some statement that you can get out of the classification report? What would be some insights that you would get after you print out, say, the classification report?
It is doing well for class 1 and
Okay.
poor for class 3.
Okay,
Not
great.
so good for class 3.
All right. So that is exactly what we'll focus on. So once you build your model, you can get the classification report, you can have a look at it, and then you can say these are the classes for which my model has performed well, and for these it has not. And since it gives all the evaluation metrics in one go, this will clearly tell you what is the next sort of direction to take. Now here what you can then consider is you can filter out, say, the samples of the class. Now here we have a low precision for class 3. So we can filter out the samples for class 3 and see why the model is performing poorly. And then you can try out the different methods that we previously discussed. So you can either consider upsampling this class to match the number of samples that are present here, or you can consider making use of class weights. So these are some options on how you can proceed once you get this classification report. Okay, any questions on this?
What are class weights?
What are?
Class weights, you said?
Yeah, class weights are, so we'll have a look at, say, logistic regression. So it allows us to weigh the samples that are there. So it takes into account how many samples are present, and based on that it gives importance to these individual samples. So whatever predictions it makes, it takes into account the weight that is assigned to it. Now, yeah, is there a question?
Sorry sir, what are we discussing today?
Today is going to be just week 7 content, which is on evaluation metrics, and the revision for the OPP session will happen on Thursday. So maybe since this is a short week, maybe for the last 20-30 minutes, I'll talk a bit about the OPP. But formally, we'll discuss OPP revision and the pattern and how things will be on Thursday.
On Thursday?
Yeah.
Okay.
All right. So coming back to this, so for logistic regression, you can see there is the option for class weight. The default is none. That is, it does not weigh anything differently. But when you use balance, what it is going to end up doing is that it is going to take into account how many samples are present. And based on that, it now gives a weight to each sample. Okay. So this way, when you calculate, say, your accuracy or F1 score, you're also going to multiply the weight that is there. This is similar. The idea is similar to how it was there in voting classifier. So now, even if it is lower class, your model is going to, if it make mistakes on the class that has lower number of samples, it is going to punish itself more and make sure it gets it better in the next iterations.
So, sir, in the example which the previous confusion matrix, can you show that?
Yeah.
So here we were not doing so well in class 3. So
Correct.
will the weight for class 3 will increase?
Yeah, no, if you make use of balance, the model during training itself, it'll take into account that there is one class with lower number of samples, but it is sort of equally important. So we might see an increase in model performance because whenever it now makes a mistake, maybe in the next iteration, it'll end up giving better, it'll end up coming with better weight so as to focus on this class as well, so as to increase the number of, see, in general, it wants to increase the number of the true predictions. Now, when you make use of balance, it is not just going to care about the overall numbers, but it is going to consider it a little more individually as well. So this is a very small sample size. So if you have a very big imbalanced data set, which I think might be the case with the second Kaggle assignment, that is where you could try something like this. You could try giving it balanced and see if it helps improve your model performance. Have any of you started the second Kaggle assignment? Okay.
No, sir.
What is the deadline for that, sir?
The deadline I think is 23rd or so. It should be there in the portal. I think it's
But 19th is OPP end.
next Wednesday.
Okay.
Yeah, OPP is 19th, which is why it was released on Friday itself. And in general, you would probably need maybe under 10 hours to work on the assignment. Yeah, the deadline is on July 23rd. So with this, you are going to get time before as well as after the OPP. And since more or less the code snippets that you need to practice are the same, doing the assignment will help you for the OPP and vice versa. The OPP prep should also help you get more comfortable with the code and you'll be able to write faster. So even for the second assignment, the overall structure is the same. So you're first going to identify data types and then describe the descriptive features you want to print out, and then handling missing values, outliers, duplicates, and such. Then, of course, pre-processing, visualization, model building, and evaluation. So the rubrics on which you're going to be measured is the same. So roughly, the structure of your notebook also will end up being the same. Which is why just to make submissions, it shouldn't take too much time, but I will definitely urge that you spend more time in these Kaggle assignments so that you can get better at the subject and also do well in the project subsequent. Okay, so that was one thing. So this is broadly what we have for evaluation metrics. We'll just have a look at their implementation using sklearn. Any questions about whatever we've discussed today so far? Okay, all right. Give me just 1 minute. Okay, so let's try out a classification data set. Okay, so among class, there are plenty of, these are a little small data sets, so we'll try out the breast cancer data set today. So, okay, how do I load the data set? What should I pass here?
As frame equal to true and xy return xy equal to true.
Okay, and what do these two things give me?
Return xy gives the label and the matrix, and as frame gives the panda.
Okay. So yeah, XY separates it out into labels and the target, whereas as frame gives it as a pandas data frame. Now, as you can see, the number of samples here are very low, but let's try out the different evaluation metrics in this one today. Okay, how do I see how many samples are present in the target label? What is a command for it?
So
Shape.
by using the shape,
Okay. This tells me that there are 569 samples. I want to know how many samples are there in each of the classes. What can I use for this?
But value counts.
I can use value counts. And here you can see there are 357 in one class and 212 in the other. So once again, you actually have to see what this 1 and 0 mean here. So one of them will be for, I think, malignant, and the other for what the benign. Yeah. So we'll have the two things here. So this is something that you have to be careful about, especially when you are giving insights. Okay. So next, say I want to train a model. Before that, I want a validation set. For that, what should I do?
Train test suite. Train test
Okay.
suite
And where can I import it from?
from model selection.
Okay. What is the syntax for this?
X train, X test, Y train, Y test.
And then,
Train test. X, Y test size.
okay, let's go with say 0.2.
And the random state.
Okay. So random state is again something that is very important in terms of your say assignments and the OPP. So not passing the random state or giving a wrong random state can end up giving you entirely different answers. Okay. Uh, let's start with the logistic regression model itself. In what is logistic regression present?
Linear model.
Okay, and now what is the code snippet for initializing a model?
LR equal to logistic regression.
Okay. Anything else I need to pass here? Okay. I'll
Random
put a
state.
random
Random
state.
state.
Why do I need a random state here?
Because
So random, yeah, you know.
uh,
So this is on how this is solved. So if you see the logistic regression one, we should have different solvers here. And when you have the stochastic gradient based methods, that is where there is an aspect of randomness, because you might not always end up trying out the same samples. So the random state comes into play there. Okay,
but
so
logistic regression does not have stochastic, right?
yeah, you can use different solvers, right? So
Okay,
that there
okay.
is stochastic.
Okay.
SAG and SAGA are stochastic method.
Okay.
So there is some suggestion here. So you can use liblinear for small data sets. We'll try that. We'll change the solver to liblinear. Okay, and what do I write here?
X train, Y train.
Okay. So we have the model trained, and now if I use score, what is the value that I'm going to get?
Accuracy score.
Okay, there's the accuracy. And in the case of regression problems?
R2 score.
Oh, good. So we'll also try it on the test data set. Okay, there are some comparable
So
scores.
here I have a question. We have fitted the model on X train and Y train.
Right.
Still, why we are not getting a perfect score with the for X train, Y train? We have fitted the model with X train, Y train only, no?
Yeah, but logistic regression is not a model that can get a perfect score always. So in the sense, it is a linear model, And now take the case where you can think of it this way. You have, say, non-separable samples. Now, take a 2D plane where I draw some points. Like this, you have your XY space. I have some green points here in a circle, and in between I put a red point. Now, will you be able to draw a line which separates them
No.
clearly? Yeah, right. So along those lines itself, logistic regression is something that, of course, these things on training data, there will be some amount of memorizing, because it is going to try and get the weights to match that is there in this. But there will be some samples wherein it will be these outlier-like cases, or it will be very close to the other class, wherein even if you are getting the score on the training data, you might not necessarily manage to get a score of 1. Can you name a model which can get a score of 1?
Perceptron?
Can Perceptron get a score of 1?
Because it is completely linearly separable, right? Perceptron.
No. So Perceptron also requires the data to be linearly separable. So if the data set is linearly separable, then your Perceptron will give a score of 1. Can anybody think of any model which will...
Maybe decision trees.
Decision tree.
Perfect. So decision tree gives it, but why decision tree?
Yeah, if there is an unlimited depth.
So what happens if there is unlimited depth? What exactly is happening?
Every
Overfitting.
there will be an overfitting, and every data point will get classified.
Right. So with these things also, we have to try and give very detailed answers as to why that can happen. So you're right. So the nature of decision trees is that it is going to ask a question, make a split based on that, and then it will see the samples and assign a class to it. Now, if I don't limit on the depth that it can go to, it can pretty much ask one question for every single data point, right? So that way it can go to maximum depth, forcing itself to ask questions based on the features of every data point. And then in each leaf, it can have a single point also if needed. That way it can achieve 100 accuracy. Again, with this, there is a scenario where what if you have, say, erratic data, wherein all the features are same, but for 2 samples, all the features are same, but they have different labels. So you might have some mistake in the data. In those cases, again, it will depend on how the underlying implementation is done, and yeah, you might end up having some sort of issue there. Okay, so let's now that we are here, let's just train this also.
So I think your screen is not visible. Is it for me only?
Or is it not visible?
No, sir, it is visible. I think
Now
he
it is
has some
visible, sir.
problem.
Now it is visible.
Okay. Let's see how it performs. Yeah, so you can see, right, it gives a score of 1. Is that okay?
Yes, sir.
All right, so continuing on, let's print out the evaluation metrics. Where can I get them?
Dot matrix.
Oh,
Sklearn dot matrix.
yeah. Oh, is my screen frozen?
Yes, sir. It becomes frozen for some time.
Okay. Is it for everybody? All right. If it happens again, let me
Yeah,
know.
yeah.
Try rejoin. Okay. So what do I need to? How do I calculate the accuracy?
Accuracy,
What do I need to pass in here?
accuracy, y test, and prediction on y x test. Y test, y test, and DTC dot predict x test.
Okay. And how do I
So
get
there's some issue with the connection, I think.
Yes, sir. Your voice is breaking, sir.
Okay, let me just change my network. Hello, is it any better? Is it clearer now?
Yes, sir.
Okay, all right. So why is this error there?
I think it's accuracy score. I think it is.
Yeah, you're right. It has accuracy score.
And precision also, I think it is precision score. I don't know. I don't.
Okay. So again, it is giving the same error. So this is these things you don't need to remember. It will anyway be there in the document.
Recall also, I think.
Okay. It has worked. Let's print ACC. Yeah. Does it match what we got? It should. On the test data, you can see it is 0.9561. We have the same value here. Now, this is one way wherein we pass the true label and then the predicted label, we have passed it like this. Instead, the common way to go about this is to first get the predictions, wherein we have ypred is equal to model.predict x test, and you can simply do y test comma ypred. What is the model? It is LR. So we have this, and the same syntax follows for the other ones as well. So now I can do in precision score of. So one thing you have to be careful of is which one comes first, whether it's the true or the predicted ones. So you can always check it via the documentation. So yeah, the first one to come is y true, which in our case is y test, and y pred, which is what we have predicted. Okay, so that is precision. We can simply extend this to. Okay, so these are the values. And as I said, we can just get this in one shot by making use of the classification report. So where is classification report present?
Metrics only, I think.
Okay. Okay. Now how do I correct this? What should I do for this?
So print.
Print.
Was there any other function that you'll recollect used to print it weirdly, and then you have to use the print function? Just checking if you have practiced enough of coding. So if you use the describe function also on loading these data sets, it prints it weirdly until, or rather it prints it in a different format until you use the print function. Okay, so here we can see there are so many things we can infer from this. So firstly, we see the accuracy was 0.9568, so it is rounded off, so we get it 0.96. And then we have precision, recall, and F1, which are 0.95, which is nothing but this one. 0.98 again is rounded off to 0.99, and 0.96 is rounded off to 0.97. There are 71 samples in class 1 and 43 in class 0. So this again should tell you whenever you use precision, recall, and F1, it is primarily calculating it for class 1 and not class 0. Okay. So that is one
So
thing.
you said DESCR, right? DESCR, that is
Describe
describe or DESCR?
this one. Yeah,
Yes.
yeah, I was referring to this one.
Ah, yes, sir. Yes.
Yeah. Description, I think it is. Description of the data set. Anyway, so the classification report gives a one-shot view, and we can also print the confusion matrix and see how many each has actually gotten right and wrong. So where can I find confusion matrix?
Metrics only.
Okay. Okay. So what do I need to pass to this?
Same thing, Y test, Y test and Y pred.
Okay. So what does this tell me?
39 and 70 are the accurately predicted ones, and 4 and 1 are false negative, false positive.
Right. So is there a way is there a better way to present this?
Plot it.
How do I plot this one?
Confusion matrix display.
Yeah. So we can make use of it is this. So to call confusion matrix display, we can then pass in the confusion. This should be sufficient. I think we have to plot it. There are different ways to do this. You can even choose to plot it using matplotlib. And then have this in some so here we have it. So this is a much nicer way to present it. This is the images that we saw in the slides also. And we can, of course, see the data set here. This makes more sense when we have larger data sets wherein it can give us a lot more and better information, so to say.
So, in the lectures, the professor has used some other method to display the confusion matrix, right? I don't recall what it is, but it is different from this one.
Yeah, we can. You don't need to use matplotlib for it. So we can run the code snippet from the documentation also. Okay, this also makes use of it. In which lecture was it there?
In all lectures, he has displayed that confusion matrix, but he
Week
has
7
used
lectures.
from predictions. That the second one, from predictions. That
Right. That is just a different way to get the same thing.
from predictions and from estimator, there are two ways.
Right. So this is wherein you make use of the model to then give the values. This is what we have done, wherein we have taken the predictions and then passed it. So you can see the two of them here. Yeah, the first one is where you give it the estimator and your x and y and make use of that. The second one is the way we have gone. We have passed in the true labels and the predicted labels. Is that okay?
Okay, sir.
Yeah, for this also they might have the code snippet. Yeah, there is the code snippet. You just need to pass these three things. So this will only take care of the sort of, it will take in the classifier object and then try it out on the test data. That is sort of the only difference.
So after training only we can do that, na? After training first and then
Correct.
you
So
get
this
it.
is where you train, and this is just skipping the part where you make the predictions. This is telling you only take the classifier, you take my test data and its actual values, and you do the predictions. So here it doesn't explicitly use predict. If you see the code snippet here, it doesn't explicitly do predict.
Just like it is using the score method, I think. Score whatever. Uh,
Yeah, so that is
just like
fine. That is okay. So it's just two different ways to get the same thing. All right. So this was primarily what is covered in week 7. Any questions on what we have discussed so far? Okay. All right. So I'm actually going to end the session a little early today. If there are no other questions, Thursday session we'll talk more about OPP. Yes, Naman.
Uh, sir, it's not related to today's session, but I
Yeah.
wanted to know, sir, what all shall we prepare for the upcoming OPP?
Okay. So OPP. Okay. Let me just give a brief of the OPP today. I'll pretty much be repeating the same thing on Thursday. But put it out here. So the OPP will have two parts. So first is pre-processing. The second one being model building. For both of these, you'll have separate data sets, wherein you'll be given links to the data set. Of course, different students can get different data sets. There are multiple versions. I think 3 versions are there. So depending on what version you get, you have to download the data set and then upload it in the Colab environment. Now, the Colab environment, specifically a Colab file will be created for you. So you will have to be working on that Colab file itself. You alone will be given edit access to it. So you download the data, you upload it there, the pre-processing part, and then you answer all the questions that follow. Now, when it comes to the pre-processing part, so this will have the pre-processing part will have first is to sort of just see and explore the data. So explore the data in the sense how many, say maybe it could be about data types, it could be about say mean, median, mode, it could be about some specific uh, data points that satisfy certain conditions, wherein you might need to filter things. So for this, I would say you have to be comfortable with exploring, taking parts of the data using pandas. So maybe it could be using the LOC function or the ILOC function or whatever method you want to make use of. After this, it will also have things like scaling, comma encoding. Then you'll of course have missing values. So for missing values, it could be different imputation techniques. So whatever is there as a part of syllabus, you should be ready with it. And what else comes as a part of pre-processing? Yeah, so mostly it will be around this. It could be say duplicates, and it could be outliers. So this is why I was suggesting that the Kaggle assignment also, it helps you with the same parts of the code anyway. So roughly, it could be these things in pre-processing, and I would stress on being comfortable with the usage of pipeline. So the above, but with pipeline, comma, column transformers, and so on. Are all of you here comfortable with pipelines and column transformers? Do you want me to show it again in the next session? Can I get a show of hands if you would want me to cover it? Okay, all right. So just make sure you practice this part, and then the second half is model building. Model building, as it says. So now here, what we end up seeing is many of them might get stuck here somewhere, wherein they can't do, say, the scaling, encoding, or even handling missing values. Then you can at least attempt the second half, which is going to be entirely on model building. So the model building will of course involve this basic step of calling a model and fitting it as we saw here, but it could be a bit more than that. It can have you do, say, some form of feature selection. It can combine with maybe some other form of feature transformation, where you might need to create some features and then build models. And then once you build model, some amount of interpretation of that model. So it could be what was your, say, important features, what was the weights that you got, so on. So where can you get something like feature importance? Say you have trained the model. How would I know what are important features? So
The coefficients, the higher the
correct.
coefficient, more important it will be.
Correct. So depending on model, you'll have it either, say, in coefficients, or it might even be called feature importances itself. And in terms of SQL and documentation, these things come under attributes. So if these things are asked, now for example, say from SQL, I think it's the syllabus is weeks 1 to 5, so it's only up to regression models. I think it's about 1. So it is not going to be just a straightforward fitting of the model, it will be a combination of things. Especially stress being comfortable with making use of the documentation layer. So if you see, there are parameters, you might be given certain conditions. Say this one has only one mainly parameter in terms of fit intercept. If it was, say, a decision tree regressor, it might be said, modify this in terms of samples, this in terms of the depth, and so on. And later on, you can get which are the important samples based on the coefficients, and these are present as attributes. So now, if I would have trained a model, say it was also called LR or something. Once it is fit, I could have done LR.coef like this, and it would have printed all the coefficients. Okay, so this way you should be, you should know how to make use of the documentation to answer. If you are set with this, that is getting parts of the data using pandas, the use of pipelines, and then making use of the documentation this way, you don't have to worry too much for the OPP. So you'll be given a mock OPP in a few days. You can try that out, but make sure you don't use anything else. Just use the Colab environment for it, and try and get whatever you need from this environment itself. Practicing helps you with time, because there will be a good number of questions for 2 hours. So if you have not practiced enough, you might not be able to answer all questions. But even if you have done the bare minimum amount of practice, you should be able to go through things fairly quickly. It will also include things a bit like, say, hyperparameter tuning and so on. Are there any other questions?
So for feature selection, what should we do?
Has feature selection part not been done before? So it is, again, most things in sklearn follow a similar pattern. So there are different ways to do feature selection. You can do it on the basis of variance. You can do something called as recursive feature elimination, and then the first one is variance threshold. Recursive feature elimination can be done either through some metric, or it could be done through some model. So this way there are a few different methods. So you will be given what specific method you have to follow. If a question on feature selection is asked, then it will tell you do it based on, say, variance threshold, or based on some estimator. So this is based on variance threshold. So wherein you have your features, you pass it, you do fit transform, and then it will have removed those features which have very low variance. Now the way you can practice this is you can create your own data set like this. Let's maybe run it here once. And this will be an issue for this. Let's just see. Okay, as you can see now, only two of the features are remaining. The first one is not there. Now this is because the variance for this guy is almost all the values are the same, right? So the default, okay, they've mentioned a threshold here. Is zero point 0.8 into 0.2, 1 minus 0.8. Yeah, so this is what they've gone for in this particular example. And based on this threshold, if this does not satisfy the condition, wherein if its variance is lower than what is given here as a threshold, then that column will be eliminated.
So it is
Then I-
0.8 multiplied by 0.2, right?
yeah. So this will also be given to you. What is the value that your threshold that you're supposed to take? Is there an issue? Okay. Um, let's try one more column here. Again, I'm adding all of them as one. So this has basically no variance, right? Yeah. So you can see this last column also is not there. However, if I sprinkle a few zeros in between, let's see if this should bring in. Yeah. So now the third column is retained. So this is the variance threshold method. Is this okay?
Yes, sir.
Yeah, so
Yes,
this
sir.
way you'll have different methods. So then there is univariate feature selection, which again has three parts within it. So this is to remove based on again certain conditions. Select k best again makes use of a few statistical measures also. So you might be asked to make use of do feature selection using select k best, but you use certain scoring functions. So here the default one I think is F classifier. So there should be a few more. Yeah, there is Chi2, there is mutual info classes, and these things will vary depending on which task you have. So for regression, you'll only have F regression and mutual info regression. So this way you'll have to know how to make use of it. So this select k best also, now you'll be given a document with the mapping of the modules and the specific functions. So you'll know that select k best is there in feature selection. So how you would go about it there is, let's say from sklearn dot model selection, no, this feature selection, sklearn dot feature selection, import select k best. This capital S, capital K. The specific document, I'll show it in the next session. So what is wrong here?
It is
Okay, there's not.
continuous
So,
without.
yeah. So you'll seeing the question. The question will tell you use say select k best and select the top whatever features. So if you don't know how to implement or if you've not implemented it, the first thing you want to do is you want to go to the PDF file that we have provided to you. There you are going to see that in this module this is present. Then you can do this select k best question mark. You're immediately going to get the code snippet. Then we would have told you use a score function, say some whatever mutual info regressor or F regression. We would have specifically told you what to use. That information also is present here. So you just copy this, and then you see what is the. Or you can actually even get the code snippet first. From this, you copy this guy. You paste it here, and then here you tell what is it that you need. So instead of Chi2, maybe you want to use, let's use F regression. Something like that. So you're going to pass in X and Y here. And here you don't have 20 features. So you have to pass in whatever number of features and target that is there. So this is how you would run the feature selection part. Now, as I mentioned, this will be part of a pipeline. So within the pipeline, you might have this as one option. So you'll have some feature selector, and then you're going to write select k best, this part, and then come after feature selection, maybe you have model building. So here you'll have your linear regression model, so on. So learn how to combine different things within the pipeline, and so on. Okay. So this is the feature selection part. Now this can even be combined with hyperparametric tuning. I think in one of the sessions I showed how to make use of hyperparametric tuning with different parts of a pipeline, right? I
Right,
think it
sir.
was in the week 5 session.
So, sir, this X new will contain the 20 selected.
Now I should have had more features than this here, and then if I had more than 20, then it would have selected the 20 based on this and given.
And X new, if you print, then X new will contain that matrix containing the 20 features, right?
Correct. Whatever has been selected, it will end up having that here. Is that okay? So that is the part. Models plus, say, feature selection plus hyperparametric tuning. It can be asked in any of these combinations. And then attributes of the model. So this is broadly what will be there. Again, we'll discuss all this in detail on Thursday. But yeah, if you're comfortable with these things of documentation, pipeline, and pandas, it should be good.
So if there's a pipeline and we do a feature selection and fit the training and test train data set, it will automatically select the features for the test also, because
It will do that. So you have to do pipeline dot predict later.
yeah, if it's a part of the pipeline, no?
Yeah. If it is as pipeline, that will take care of all of that.
So explicitly we don't have to do a feature selection and eliminate from the test data set. The pipeline will take care of it.
Yes, the pipeline will take care of it. So when you get your when the mock OPP is released, I would recommend just have a look at the questions. Don't just try coding out yourself and just compare it with the final answer. Don't go to check what the actual solution is or what the code is through LLMs or anything else until you are able to match the answer that is provided. So that should clearly help you understand these things in detail. Okay, are there any other questions? All right. Okay, in that case, I'm going to stop streaming. If you have any questions regarding the Kaggle assignment, the OPP or any of the course content, we can discuss. If not, I'll close the session.
Thank you, sir.
Okay, then, yeah. Thank you for joining.